Good evening, everyone. So today we'll welcome to class 7 of stochastic communication and stochastic control and communication. So yesterday we were looking at how to find optimal policies. Yesterday we were looking at how to find optimal policies. So optimal in what sense is you uh, minimize the average cost, where the cost has a specific structure which we have defined throughout is g of xn plus summation I equal to 1 to n minus 1 g of I xi ui wi, where these are your state related costs. This is your terminal cost, and xn's are your state in the system. UI is your control action or your decision that you need to take at each and every step, and wi is your randomness in the system. The xis are governed by dynamics of the system, where you uh, go forward in the state depending on what action you choose and depending on some randomness that happens in this. So because of the randomness here, this expectation is over the distribution of the randomness. Because you have the, the next step, the next state is random. So and that randomness come from WK. So your next step cost would be random. You don't know where you'll end up in the next step, even if you know what control action you've taken, right? So um, this is how your cost function looks like. Uh, Yesterday, what we saw was so this is your basic stochastic control problem. We saw that stochastic control problem has many similarities with the shortest path problem. And we found one pretty interesting thing in the shortest path problem was, suppose, so I'll reframe the shortest path problem. So if you want to go from A to B, right? Suppose you can go, there are multiple paths to go from A to B. Suppose I say that this is your optimal path. Okay. Now, as you can see, when you are at this node, you have the power of making a choice of either going through this node, through this arm, or through this arm. Now, if I repose the problem, if I repose my problem and I call this new node as C, and my new problem is um, what is the shortest path from C to B? And I know that this pink marker is the shortest path from A to B. Then this has to be your shortest path from C to B. This can't be your shortest path. This can't be your shortest path. This can't be the shortest from C to B. Because if this is the shortest path from C to B, then this is not your optimal path. Then the more optimal path would be this, right? But that is a contradiction. So if you know the optimal solution of the whole problem, then the sub-problem optimal solution would be a sub-part of that strategy. Right? This is an observation. And why does this happen is because the cost incurred by the problem defined in shortest path problem is also additive, right? So as in the stochastic control problem, where you choose actions at each step, and based on those actions, you get rewards. In the shortest path problem, what happens is you choose at each node, you choose which um, link should I travel. And based on that, once you choose a link, you either get a minimization of distance problem or a minimization of time problem. So you are either trying to minimize the distance you want to go from A to B, or you're either minimizing the time that you want to go from A to B. Okay, so I'll just do a recap of what I was explaining in the last class. In the last class, I was explaining parallels between stochastic control problem and the shortest path problem. So uh, first, I'll just go through what the stochastic control problem is. Stochastic control problem is you have a system with dynamics fxk equal to xk plus 1 equal to fxk uk wk, where xk is your state, uk is your control, and wk is your randomness in the system. So xk is a random variable because you have a random variable in wk. So trajectories are random. You have the choice of taking what UKs you want to be. So you have the control of choosing UK. Okay. And what is that you want to minimize is you want to minimize the average cost. This average cost, you have two parts. One is a terminal cost, which is at the end of the trajectory, and then stage-wise cost, where each stage-wise cost comes because you are at some stage, and because of that state, you are paying a penalty, or you're paying some cost, and because you have chosen control action UI, you're paying some amount, or that you're paying a cost, and then because of the randomness in the system, which induces randomness, and that randomness you will see in the next uh, positive, right? So you're trying to minimize this average cost, and yeah, and now so this is your basically this is your stochastic control. You have to minimize your cost of this form such that your dynamics are this. Yeah. So next, the shortest path problem. The shortest path problem is basically, suppose you want to go from A to B and you have multiple paths that you can choose. Okay, I'll do one thing. I'll erase this. So you want to answer the question of what is the shortest path from A to B. So suppose I tell you that the shortest path from A to B is, this is the shortest path from A to B, right? From A to B, you can go to multiple routes. You can use the above one, the middle one, the below one, or some form of that. I tell you that, okay, this is your shortest path to go from A to B. Now, that I've given to you. Now I repose the problem as I don't want the shortest path from A to B. I want to find the shortest path from C to B. What is the shortest path from C to B? Right. The shortest path from C to B, and C is an intermediate node in the optimal path that I've given you. So if you say that the shortest path from C to B is this, then we have contradiction. Because if this is the shortest path from C to B, then instead of going for A to B, instead of going this way, you would have gone this way. But you already know that this is your shortest path. So this can't be a shortest path for C to B. This has to be a shortest path from C to B. So the observation that we have made here that is that in the shortest path problem, if you know uh, the optimal path to go in your whole problem of A to B, now if you're allowed to choose a sub problem in that path by keeping your terminal state constant, then also the sub problem's optimal part would be a truncated vector of the total path. Right. It can't be something new. It has to be from the original. It has to be a part of the original optimal solutions. So we will actually use this to come up with the dynamic programming algorithm to find optimal policies for stochastic control. And why is stochastic control similar to the shortest path problem is because shortest path problem also has the same thing. It has a fixed number of steps. You start at some point, you end at some point. You end at 10 steps. And each step you take a decision. That decision is here in the shortest path problem. It is choosing a link. In the stochastic control problem, it could be more general. It need not. It need not be just choosing a link. And then once you choose a link, you have to pay the penalty of either the distance or the time. So once you choose a link, either you travel while traveling from one node to another node, you have to travel some distance. That is the cost that you pay because you have chosen a link, and you want to minimize the either the distance traveled or the time you are in travel. Stochastic control also has a similar formulation, and and one of the main similarities is in the stochastic control problem, you can see the cost is added at each stage, similar to the shortest path problem where the cost is added at each stage. So uh, in the first step, you add your distance. Next, you keep on adding your distance or you keep on adding your times. So this is a similarity between the stochastic control and shortest path problems, right? So what we have observed is, so the observation that we have made here is also known as the principle of optimality. So I'll write this in a formal way. Let pi star equal to mu naught star to mu n star, mu n minus 1 star belongs to pi md, where md is your deterministic Markov decision policies. So this whole set is a deterministic Markov decision policies, Bn optimal policy. So suppose this is an optimal policy. Now suppose you have used pi star. So you have applied pi star to your stochastic control problem. Then you reach state xi, state xi at time I with a non-zero probability. So why do I need this? Is suppose here I knew that the optimal path was this, and then I took a state from the optimal path. Now, if I would ask the question, what is the optimal path from D to B? If I had some other link here, then uh, I don't know the answer. I have to recalculate again. But because I have chosen a state which lies in the optimal path, I can say what is my optimal policy from. And here in the shortest path problem, there is no randomness. And since in the stochastic counter problem you have randomness, you have to add that if you use this optimal policy, then with some non-zero probability, you will reach an intermediate state xi. So there should be some non-zero probability of reaching that state. You might reach, you might not reach, but there should be some non-zero probability of reaching that state. So if using this, you have a non-zero probability of reaching xi, then the sub-problem where we are at xi at time I. Now this sub-problem is of minimizing your expected cost, but not from, from xn, but the external cost k is not from 1 to n minus 1. It will be from I to n minus 1. So I to n minus 1, gk, xk, uk, wk. Now this you want to find pi over this subproblem. Then the truncated policy mu I star so on to mu n minus 1 star is the optimal policy. So this is the statement for principle of optimal. So this is just an observation that we have made. The observation is that if you know the optimal policy, then any subproblem in that optimal policy, you just need to truncate your strategies so that you get an optimal for the subproblem also. Okay, so today I'll I'll try to give you the dynamic programming algo. So this dynamic programming is for stochastic control problems. I'll give the algorithm. Okay, so an optimal policy is given by if you follow the following algorithm. So first what you do is you fix jnxm is equal to gnxm as a terminal cost. So you define. So um, I'm defining these variables here as my terminal cost. So this is for all xn. Okay. Next, what you do is you define jk of xk. So this is basically like a cost till your nth step. So we will uh, go through this one by one, but right now I'm just defining terms. So jkxk is basically minimize uk. So now you're just finding what uk is. That belongs to ukxk. Expectation gkxk ukwk plus jk plus 1, the previous optimal subproblems. Uh, this and the dynamics fk, xk, uk, wk. And you keep on doing this for all cases. So you first do you are define jn gn plus 1. Then you do you calculate. So after this you calculate jn minus 1 xn minus 1. This for all xn minus 1s. This is for all x case. And then using this jn minus 1, you calculate jn minus 2, xn minus 2 for all xn minus 2. And this formula is given by this jk. right? You keep on doing this till you reach J star x0 and J0 x0. So once you reach here, all the UKs that you have gotten from deriving this, this comprises your optimal policy. So what you're doing is you're going from the back. So starting from the back and calculating all the sub problems that could lead to the optimal policy. Okay. So basically, if mu star k equal to mu k star xk minimizes this term. So I'll call this as 1, minimizes 1 for each xk and k. So you have to do this for all k's. K is going from n minus 1 to 0. Then your optimal policy pi star is mu 0 star, mu 1 star, and so on, mu n minus 1 star. This is optimal. So basically what the dynamic programming algo says is you keep on doing this iteration subproblem, you keep on solving the subproblem from the back one step at a time. And then at each step you get a UK, and then we collect all those UKs and then you place it in one place and then you get your optimal policy. All of this is for now we'll be dealing all deterministic Markovian policies, right? So I'll today we'll look at a proof for this. Okay, so proof is let pi be a policy, n minus 1 be a policy. Pi k is basically a truncated policy from k to n minus 1. This is a truncated policy. Okay. Let jk star xk be the optimal cost of n minus kth stage problem. Uh, hello.
Hello.
Yeah. You have a doubt? Hello. Okay.
Hello.
So
I
yeah.
I don't have any doubt.
Oh, okay, sure. No, I just heard something. I might have misheard. So jk star xk. So what jk star xk is your actually the optimal cost that you get while applying the optimal policy. So it's basically minimum pi k expectation gn xn plus summation I equal to 1 k to n minus 1 gi xi mu I xi w. Okay, so the optimal cost of the n minus 1 state problem is basically this. So what do I mean when I say that it's my n minus kth stage problem is, suppose in my time axis I have n divisions, right? 0, 1, 2, so on, k minus 1, n minus 1. So this cost function is going from is solving the subproblem of finding the optimal path in this line from k to n. That's it. Your terminal cost gn, your terminal cost, and then all the stages from n minus 1 to k you pay. So this is basically solving the subproblem of going from k to n. And then once you have this optimal cost, what you do is you have, okay, this k plus 1, this is k minus 1. What you do is now you keep this whole thing as jk, and then you take one step here and see what is the optimal strategy in this one step, keeping in mind that this is your optimal cost. That is what you're doing here actually. You're adding the kth step and using the k plus 1 uh, optimal cost that you have calculated in the previous step. So you're going back in a sense. You're starting at the terminal state and then you're going back calculating the optimal stage and keeping the optimal cost at each time. Okay, so this is what you're doing here, and that is what the dynamic programming algorithm tells you to do. So uh, from from the definition of dynamic programming algorithm, we have that the cost is gn plus 1. There is no other option. You can't choose anything in the terminal cost. So basically, gn star xn is basically gn xn for all x. Now, what we want to show that is we will show that gk star xk is basically gkxk. And this gkxk is coming from the dynamic algorithm. This definition. This definition. You see that this definition and this definition are different, but we'll show that basically this gk star that we have defined here and this gk we have defined here both are the same. So if we can show that both are the same, then basically solving this solving a stochastic counter problem using the dynamic programming algorithm would give you the same policy that we have used here. Yeah. So in the last class, I also told something about, I'll just go quickly through it. So I also told something about the complexity of solving a stochastic problem. So uh, yeah, the complexity is pretty large. So if you have a state space with cardinality b, so if you have b number of states and a number of actions at each time step, and you have an n time horizon, then uh, if you jot down all the policies that you can jot down and calculate the cost for each of them, basically you're jotting down a power b into n number of policies, which is very huge, which scales very huge. So as if you just have some 10 actions and 10 time horizons, you're basically jotting down 5 or 10 um, policies, which is, yeah, very large. So it doesn't scale. So it's not a good idea to write down all the policies and look, okay, if you take this action, what happens? If you take this action, what happens? So its complexity is very high. Writing down all the policies, you can't do it the hard way. So for that, we see some resemblance between stochastic and shortest path problem, and using the principle of optimality, where you see that if you know the optimal path, then the sub problem truncated optimal path should be the same. We do it in the backwards in dynamic programming and come up with an algo which shows that if you do this algo, then you are basically solving n uh, vector problems at each time, and then you get your optimal solution. You don't need to go through all the policies. You directly get your optimal solution by just solving n uh, optimization problems. I hope the motivation is clear. Um, yeah, so we'll show this, right? So induction usually starts from 0 or 1. You do the base case first and then you go above. But here what we'll do is we'll start from n. We'll start because we just have to show it for 0 to n. We have a finite horizon problem. We don't have an infinite horizon problem. So we'll start from n first. So we'll show this. We'll show this using induction. So for k equal to n, from definition, we have j star xn equal to j of xn equal to gn of xn. So this is from definition. This is the base case. The base case in um, induction. Now we'll assume that um, for k, jk xk plus 1 equal to jk star xk plus. This will assume. So this is how induction goes. You have the base case, you make an assumption, and then you compute the next step in that assumption. So assuming this to be true, you compute that jkxk is equal to jk star xk. So now I'll just write down jk star xk. Jk star xk is just minimum mu k and pi k plus 1. So basically you have is jk star xk is minimum over pi k. So I'll write this separately. So this is you have the vector pi k, which is mu k minus k plus 1, so on to mu n, right? The truncated policies, which we have defined it here, the truncated policies. Now how I'm writing this is, I'm writing this as a vector where this is mu k and this vector is pi k plus 1, right? I'm splitting this vector into two here. Okay, and now I have expectation of g and x and the terminal cost plus summation I equal to k to n minus 1 gi xi mu I xi wi. Okay. Now I'll just rewrite these terms as okay expectation of I'll I'll pull out the first term here, the gkth term. So gk xk mu k xk wk plus gn xn plus summation I equal to k plus 1 to n minus 1 gi xi mu I xi wi. Okay. Now this expectation so now this one. Yeah. So now I'll use something known as linearity of expectation. So the linearity property of expectation. So what does linearity property of expectation tell us? The linearity property of expectation tells us that expectation of x plus y is expectation of x plus expectation of y. This is your linearity property. So you can um, split the expectation over summations. So I'll do the same here, but min I'm keeping. So min mu k pi k plus 1 expectation gk xk mu k xk wk plus min. Okay, now in this you will see that mu k doesn't play a part. Only you have mu i's from mu k plus 1 to mu n minus 1. So only pi k plays a part. Mu k doesn't play a part. So this is minimum over mu k plus 1. And here also uh, pi, pi k plus 1 does not play a role here. Only mu k plays a role. Right? So I've split this vector also because the first term depends on just mu k and this last term depends on the vector pi k plus 1. So I just choose the minimization over those. Expectation gn xn plus summation I equal to k plus 1 and minus 1 gi xi minus xi w. Okay. This can be written as minimum mu k expectation of gk xk xk mu k xk wk plus jk plus 1 xk plus j star xk plus 1 k plus 1. This is the definition of j star jk plus 1 star xk k plus 1, right? Um, yeah. But we have the induction proof, we had assumed that this to be true. This is an assumption that we had made. So under the assumption that this is true, I can write this as min uk expectation gk xk uk xk wk. You can bring this inside because it doesn't matter now. Plus j k plus 1 x k plus 1. And this is basically your this definition, the definition for jkxk, right? This one. So from 1 we have min mu k. Oh, sorry. From 1 you directly have this to be jkxk. So what you proved is jk star xk is equal to jkxk. So this is your policy obtained if you follow the dynamic programming algorithm, right? And this is your optimal algorithm, like cost incurred if you follow the optimal algorithm. So the cost incurred if you follow the optimal algorithm is the same as the cost incurred, but if you follow the policy obtained using the dynamic programming algorithm. So we have shown the dynamic programming, the policy that you get from dynamic programming following the dynamic programming algorithm is basically the optimal policy. So this is one method to find an optimal policy. So now what we'll see is we'll see an example on how to solve the dynamic program. So first example that I'll show is I'll show an old example that we discussed, that is the inventory control. So we discussed the inventory control and we'll apply dynamic programming on the inventory control and try to come up with optimal policies for the inventory control. So this example I'll do in two parts. So one part I'll do it today, the next part I'll do it tomorrow. So one part is I'll just write down how do you write down all the steps of dynamic programming for any given general inventory control. Then tomorrow what I'll do is I'll take values and I'll define some assumptions which actually help in finding a solution, like a closed form solution, so that it feels more real. Like you understand, okay, if you do this, and if you take these assumptions from your real life system model, then you can come up with a closed form solution when you follow dynamic program. So today I'll just give a brief overview of how to apply inventory control, dynamic programming over the inventory control, right? So okay, before that, let me just do quick recap of what inventory control is. So you had a time horizon of n steps, right? So basically, at 0, 1, 2, 3, so on, k plus 1 to n. Okay. Uh, yeah. And your states xk were amount of inventory in your store, or somewhere with you, amount of inventory that you have. UK is amount of inventory you have to order. That is a decision that you have to make. Next, you have WK, which is a demand on the amount of or order that you get, right? So this is throughout a time epoch. This is not at a time instant. This is throughout an epoch. So basically, what happens is you have X0 here. You place an order of U0, and then you get that, and then over this time interval, you get a demand of W0. And then at this instant, you have X1 remaining, and then you place a order of U1, and then throughout the next interval, you get W1 demand, right? So how does the dynamics takes place is, so how do you get X1 from X0 is you had X0, so X1 equal to you had X0, you added U0 amount of inventory to your stock, and W0 amount of people came and took away the stock from you. So W0, right? We assume that the X1 could be negative, so you have a backlog. But then usually what happens is if you're out of stock, then you can't sell anything. So usually this is the dynamics is plus. This is a nonlinear dynamics. Not they are not linear because of this plus, and this plus is basically max of 0 comma X0 plus U0 minus W0. Okay, this is your dynamics. Uh, to just recap, this was your xk plus 1 equal to f of xk comma uk comma wk. This function was this for your inventory control problem. Okay. Um, yeah. Now we had a cost we want to minimize. So the cost that we had to minimize was UK greater than or equal to 0. So you can order stock, you can't send back stock, hence UK is greater than or equal to 0. Expectation was RXN. This is your end terminal state cost. Summation k equal to 0 to n minus 1. You had a cost R k of xk. Now this cost is for, so suppose you have x1 amount of stock remaining until the first epoch, right? Then you have to store that x1 somewhere. So this cost is basically storage cost plus C into UK. So this cost is because you have ordered UK amount of stock or inventory, you have to pay for buying that stock or buying that inventory. So C is the unit rate of the stock and you are buying UK amount. So it's basically the cost that you're paying is C into UK. And this is the cost that you have to minimize in the inventory control dynamics. So if you apply the dynamic programming here, what you do is GN XN equal to GNX, right? I'm just rewriting the dynamic programming steps. And then you find GKXK, minimize UK, expected, GKXK, WK, UK, plus JK plus 1, FK, XK, UK, WK. And then you do this until you reach J star X0, which is equal to JX0, right? So the first step is this. Your JNXN is your terminal cost. So you know this terminal, this function, this terminal cost. So first step is JNXN equal to R of XN. Now, what is this R? I have not yet defined here. This is just a general way. But tomorrow when we do the inventory control problem again, I'll define what this function is. I'll define what this function is. I'll define what series. We'll take values there and we'll see how, if you take some values, then what sort of closed form solutions you get from those, right? So your first step is done. This is your first step. Then the next step is k equal to n minus 1, right? So for k equal to n minus 1, you have g of n minus 1, x of n minus 1, which is you minimize over u of n minus 1. And you have expectation of, now it's it is the kth stage cost, right? Kth stage, you are ordering UK amount of inventory. So C into UK plus you have X n minus 1. You're in Xn minus 1 state. So you will get a cost of Rxn minus 1 plus Jnxn. But Jnxn you know is to be Rxn. So it's Rx, right? So intuitively what this means is in the timeline, you are at n minus 1 and you're trying to find the optimal strategy of going from n minus 1 to n. You're just doing one step optimization, nothing else. You forget about the whole problem of going from 0 to n, and you just want to see, okay, I want to go from n minus 1 to n, then what is the optimal step that I can take? So you're doing just one, you're solving one optimal problem and you're finding out just one function, not a whole string of units. But then going from n minus 1 to n, you need to know all the terminal costs that you can have at n. So what will happen is, suppose at n, suppose there are two states, n can go to x0, at n you can be x1, right? And x0, if you are at x0, R of x0 is 10 and R of x1 is 5. Then you would want to go to R of x1 because you're trying to minimize the cost, right? So that this will play a role in finding out this expectation, because now from going to n minus 1 to n, you would want to go to Rx1 more than x0. So you will choose an action which will push you to Rx1 rather than Rx0. I hope that intuition is clear. Okay, so this is the intuition for this k minus 1 step. I'll I'll just expand this out more so that tomorrow when we come back and solve the problem, it will be just putting the values and solving the expectation. That's it, nothing else. So this could be minimize un minus 1 greater than or equal to 0. Expectation cun minus 1 plus r xn minus 1 plus r xn. Okay, here I want you to see that this is not random. And this is also not random. The whole randomness comes from here because xn equal to, you are at k equal to n minus 1. You know what state you are at n minus 1. And then from that state, you're going to n. Xn is random. Xn minus 1 is not random. So xn is the dynamics xn minus 1, mu n minus 1, wn minus 1. So randomness is here. So these both terms can come out of the expectation. And you get minimum un minus 1 greater than or equal to 0, c un minus 1 plus r xn minus 1 plus expectation of r. Now xn you can write as xn minus 1 plus mu n minus 1 minus wn minus 1. So uh, this basically gives you the expected reward based on the action that you're choosing and on what state you'll end up. So here, if Rx0 is 10, and you want to minimize this. So you'll choose an action such that you don't end up at n0, x0. You'll choose an action such that you end up at x1. This minimizing this expectation is doing that. Okay, and now you'll see that this rxn minus 1 doesn't depend on un minus 1. So basically you can take out rxn minus 1 plus minimize un minus 1 greater than or equal to 0, cun minus 1 plus expectation r xn minus 1 plus un minus 1 minus wn. You this is we'll simplify till here. Tomorrow what we'll do is we'll come up with some values of all these, and we will solve and see how taking what action gives you what results, right? So you find this, you find this for all states. So what you do is you first fix, suppose in k equal to n minus 1, you have three states, x0, x1, x2. Then you first fix x0. Then you get jn n minus 1 x0, and you calculate this for x0. Then what you'll get is you'll get a mu 0. You'll get a value here. So that value is, so basically your optimal x0 action is, you'll get some mu, you'll get some action, say ua. Similarly, you do it for x1, you get mu b. Sorry. So you calculate jx0. Jx0, suppose you get some 2.5. Jx1 you get 1.5, and jx2 you get some 0.5. Then yeah, you will see that yeah, we will do this tomorrow. I forgot what you say. Just give me 1 second. So yeah, so what will happen is you, so first you calculate for j x0, so jn minus 1 x0, and then jn minus 1 x0. Suppose at this x0 you can take three actions. You can take ua, ub, uc. Then for each action you will get a optimal cost. So this cost you're not at minimizing, you'll just get this cost. So for suppose for UA you got 5.1, for UB you got 2.1, and for this UC got 0.5. Then if you're at x0, you choose UC, because you choosing UC is what minimizes this function, right? So now you have the mapping saying that mu star x0 equal to UC. And you start at n minus 1. That is your optimal policy when you're at n minus 1. Now, similarly, you do the same thing for, you do it for jn minus 1 x1. And suppose when you're at x1, you can take only two actions, mu a and mu b. And suppose you get 0.5 and 0.2. You calculate this expectation for mu a and mu b, and you get 0.5 and 0.2. Then you choose this. Then you get mu n minus 1 star x 1 is 0.2. So now what you're calculating is, if you're at time n minus 1 and you end up at x0, then choose action C. If you're at n minus 1 star, n minus 1 time step, and you end up at x1, then choose UB. This is UB. Choose action B. So basically you're getting the function of mapping from states to the actions. Okay. At each step. So now this is your optimal for jn minus 1. Now similarly, you have to find for uh, k equal to n minus 2. And you have to repeat this whole exercise that we have repeated here for k equal to n minus 2. And then similarly, you have to do it for k equal to n minus 3, and so on. And you have to go till k equal to 0. So this is a dynamic programming, and this is how you write up the recursions in dynamic programming. So you solve one, and then you use that to solve the next, and then you use that to solve the next, and then you use that to solve the next. Okay, I'll stop the recording.